This the industrial perspective of energy supplier, EDF, and benefits also from an experience more as an academic at CIRED, where he worked on integrated assessment models. That was the subject of your PhD, right?
Yeah.
So the floor is yours.
Thank you. Okay, just tell me if it doesn't work. Thank you for inviting me here. So I will express only my own view, obviously, and not the ones of EDF or something like that, because I think EDF has no corporate view on scenarios or things like that. So obviously it is personal, and I will try to mix my previous experience as a modeler and a scenario producer with my more recent experience of a scenario consumer or scenario user or scenario reader. I became not more skeptical, but more aware of the very difficulty to produce scenarios that are sound for decision maker. I think Patrick has shown you yesterday that there is a huge amount of material in terms of scenarios, modelers, models, trajectories, storylines, etc. And it is very difficult to swim in this scenario ocean. And it's even more difficult, I think, for a decision maker or stakeholder that is not himself a modeler to read these scenarios and to take something of this scenario. So one solution is, like our colleague from PSR, to build your own scenario, because you know exactly what is inside, and so you can just play with it, and you know how to argue about why you choose something in one trajectory when you choose something else in another. And apart from this strategy, it is very difficult, I think, to build something clever for your company from external scenario. And so I will try to give you some very broad consideration about scenarios, and we can enter more deeply in some points if you want. But I will not present any scenario precisely here, because I'm not a scenario producer, and EDF is producing some scenario internally, but obviously I'm not entitled to show these scenarios, which are strategic materials for the company. So first, what do we need as an energy supplier, provider, producer? The first thing we want to know, and we want to update very regularly, is a broad view of the possible future state of the world. And I insist on the word broad, because at this stage we do not have to to restrict ourselves on uncertainties, on disruptions, etc. in the future world. And so we have to watch over a lot of different things, especially economic growth and demand and investment resources, about the evolution of technologies, the evolution of lifestyles, especially on mobility, for example, but also on buildings, on specific uses. I don't know, perhaps tomorrow it is robots and automatic devices in the house. We have to take care about resources, and the resources we know, the resources we think we know, and the resources we do not know. We have to take care about the environment and sometimes to the fat tails of the distributions. The climate people know that very well. And we have to take care about institutions and the future of our world or regional organization. And I like very much this graph, which comes from a PhD of Magali Humber, and which was shown by the administration during the national debate. It makes us very modest about our capacity to predict the future and to assess real uncertainties. Because here you see the consumption trend forecast at different dates in the past. And the forecast are the lines, and the real consumption is the dotted line here. So you can see that the best forecast is at all times just a tangent of the curve, okay? But sometimes we had a very optimistic view of the growth, and there has been a big disruption at the first oil shock, obviously, you know that. And after that, as the curve is relatively flat, we can expect that forecasts are better because the tangent is just the curve. So it's, you see forecast is really simple. And if I can give you an advice, when the curve is flat, you can make forecast.
What does it show, this figure?
The consumption, the total energy demand in France of energy, sorry.
Total energy.
Yes, sorry. And it is in megaton of oil equivalent. It's now it's final energy. So the second thing we need is not only a broad view of future states of the world, but also assessment of strategies and public policies. And obviously the assessment of our own investment strategies in different states of the world. So in fact, we want tools and methods to be able to do these two things consistently, to model the future state of the world and to assess strategies or public policies. It is really important for a company like EDF because we are in constant dialogue with the public authority to discuss and to build optimal strategies, from an global interest perspective. Okay, so there are two layers of thinking. One is public interests, because we are a public company, and one is our own investor strategies in France, but also in Europe and in the world. To do that, we have several available methods, and not only modeling. The first one is narratives. We can just discuss about storylines and what could be the future. At this stage, it's often at this stage that we have a lot of imagination. And when we go to modeling and complex mathematical programming, imagination is restricting because we must concentrate on computation, programming, etc. So this stage is, from my point of view, very important. And one good example is the shell storylines, the shell scenarios produced each 2 or 3 years that are often very interesting for just thinking out of the box. The second tool is our external quantitative pathway. Just scenarios produced by others. It can be scenarios produced by academic people, like Patrick. It can be scenarios produced by the world community of researchers, like the stress scenarios, a special report on emission scenario at the beginning of the century. It can be the annual World Energy Outlook, which is probably the most observed scenario in the world. Or it can be the future IPCC scenarios, the representative concentration pathways, that obviously are very important pieces. And to say that, you have to look carefully at the literature and to be a bit aware of the scientific literature. It's not easy for somebody that has not been in the community, scientific community before. The third strategy is to make consultants work. Usually the industry likes this thing because you can ask exactly what you want to consultants. So for the macro side, we have, for example, Oxford Economics, which is very well known. For the energy side, we have EHS CIRA. Enerdata in France, we have also research centers, etc. The fourth strategy is to have a model to play with at home and to develop your own scenario. And finally, not the least, you can make back of an envelope or computation, and they are really important to check out what are the results of all the fourth strategy. So one of our issue, I'm sorry because these 2 or 3 following slides are 5 years old because they are just extracted from my PhD, but the message is still the same. We have an exponential amount of material in the literature. This was, I had time in my PhD, so I was just counting the number of scenarios and the numbers of models. So this was the cumulative number of publications with scenarios in it, and the cumulative numbers of scenarios available in the literature as they were put in the IPCC Japanese database of scenario, which since it has been updated in the last IPCC report that will be published at the end of the year. So you see that this curve is really exponential, and that the results are puzzling uncertainties. If really the world can be either here or here, it is really difficult, even at closer horizon. It is very difficult to build a strategy and to to be ready to be in this state and also in this state. So our question there was, are these intervals of uncertainty real uncertainties, or made uncertainties, modular uncertainties about the model, or about how they play with inconsistent assumptions? So facing this situation, I will propose you a reader's guide for external scenarios. If you have to look at external scenarios, what can you just try to understand to be able to, to assess, to have your own assessment of the scenario? The first one is the storyline. Sometimes I say the utopia which is behind the scenario. What is the implicit or explicit motivation of the modeler, and what he tried to put in figures with the scenarios? Sometimes, but not most of the time, the modeler is just thinking as an academic, just trying to see, to have a set of assumptions and to see what the model is producing with this assumption. But it's quite rare. In most of the case, there is some strategic use of scenarios, and you have to either a normative view, and you want to see how you can put in figures a normative view. For example, it can be, how am I going to set a 2 degrees trajectory, and I try to find a trajectory, or I'm sure that the society should evolve in that way, and I just put it in figures. So I would just go faster, but you can ask, for example, what are assumptions about lifestyles and behavioral change in the model? What is the future of industry, especially for Europe? Is there a further decline of industry, or is there a rebound in industry after the crisis? This is a really important hypothesis, and I think it could change a lot the face of our economy in the next decade. You also have to know the implicit constraints that the modeler has set in the model. For example, I don't want any nuclear, or I don't want any big share of renewable because of intermittency. I think that intermittency is an unsolvable problem, so I just want to avoid that. A modeler has always some kind of underlying constraint in his mind like that. For example, you have to know what is the place of electricity. So the second layer is try to find indicators to check the feasibility of, or to go deeper into the scenario. And sometimes, most of the times, a model is not describing all the set of indicators that you would like to see in the scenario. I remember when I was a researcher working for the industry, and especially for EDF, most of our meetings was about, do you have an indicators of the numbers of cars in your model? Do you describe the nth technology of coal supercritical plant in your model? Do you have the precise importations of coal from Russia to Europe in your model, etc.? And it was always the same question. Stop it, I do not want a scale 1-by-1 model of the real world. Okay, I just want to represent a world at a certain scale to show some dynamics, but not all the different indicators that you want to see in it. But it is really important, I think, to have some checkout indicators, like, for example, on lifestyle, the housing surface of buildings, the per capita travel time. I have a story on that because in our model, when I was at the CIRED, we had an input-output table. And that is a small coefficient, which is the consumption of transportation by industry, you know, in the cross-sectoral input-output parameter. And this parameter was just taken as given and kept constant in the first version of the model. And then we see that the consumption of transportation in the world was just exponential, and it was a real problem to solve the model because, and we see at the end we check that the time of travel of each businessman was superior to 24-hour day. So it was a problem. So this kind of checkout, I think, is really important. And the third layer is about policies, or broadly speaking, condition of success. You know, when you have just a strategy in front of you, do you have some information of the stumbling blocks that you have to raise to overcome, to manage to do this scenario? What policies are in place in the scenarios? What price signals? What innovation strategies? What redistribution strategies between people or between sectors? And I know there are German people here, and this is a debate currently in Germany, how the energy policies make some implicit redistribution between people or between sectors in the economy. This is really an important, it can be an important condition of success. Obviously, for the climate, international policies, international transfers between poor and rich countries have been always a subject in the negotiations. And also what policies in terms of human capital development and skills. This is without knowing the model, but even more you can go further and go deep inside in wondering what is the model behind the scenario. And this is more complicated, but quite interesting if you can do that. Just before describing the model landscape, you have some advantages, obviously, of using a model. The first thing is that you make a complex calculation that you are not able to do with your own mind, either in optimizing a strategy or simply simulating a future state of the world. And you want to check consistency of your scenario, because model has internal consistent equations, and you can check that what you project on the price side is consistent with what you project on the quantity side. For example, with your budget equation, because if the price are going up, you cannot consume as much as quantities, as many quantities as before. You can check consistency between behaviors and technologies, and it was really important in the former presentation, I think, this dialogue between behaviors and technologies. And you also, and it's in an old subject in the energy community, you can check consistency between what you project in terms of energy scenario and macro scenarios. Are they consistent together? But you have also drawbacks. The first drawbacks, if you can, is that you can spend a huge efforts to develop a model, to fit the model with data, but at the end you are not sure to have sound results. You can just spare your time. And it is quite discouraging sometimes because you just spend very much time to check that the model is running correctly, that all the indicators, all the output of the model makes a consistent picture, but at the end you say, so what am I learning new in the result? Just what is different in the result from the input of the model? Did I learn something? Can I learn something to policymakers on this model? And in fact, this is really, I feel, I know that for modelers, this is a very difficult thing. And now, as I am a scenario reader, I'm sorry to say that more than half of the scenario do not teach anything to people. They are just another strategy, another scenario which is put into literature. And so this is a very high quality demand for model work and for scenario developing. And the second drawback is the black box. Yes?
Isn't it
a huge advantage, at least, to have consistency between the figures.
Yes. Yes, if you have a model that guarantee consistency, yes, which is not the case of all the models. Yes, but it's right. This is a big expectation, at least, of the researcher, the modeler, and the consumer user, the scenario user. And the second drawbacks or risk of modeling is the black box issue. You know, it's sometimes very difficult, even for the modeler, to explain precisely what is the pathway that makes, especially in optimization work, that lead to this optimal scenario. In some cases, we are not even sure that there is only one optimal scenario. We have one result of the model, but in economics, it is quite rare to check that we have a unique solution of the model, okay, which makes probably some physicists surprised, but it's one risk of that, and if you have a black box, so at the end you have low confidence in the results, and so you can have which I call a strategic use of scenario. You just play with trajectories, one strategy against one another, but at the end it is not useful for decision maker. So this was the dark side of the modeling stuff. I will end with that. In my PhD thesis, I tried to look at all the models that were behind the IPCC database, and my conclusion was finally it's a family story. You know, you have just a few family of models which are deeply inherited from 30 or 40 years of economy and energy researchers, and I describe these five families like that. First, you have a first axis. The horizontal axis is the difference between bottom-up models, which are very precisely precise technology models. Okay. I think that the model which is behind the PSA model is a bottom-up model. You're describing the fleet very precisely. You're describing the behaviors, the motors, the weights of vehicles, etc. At the other side, you have top-down models which comes from the economic science. So they are more general equilibrium models describing the world economy and intersectoral interactions, or very simplistic optimal growth model with only one sector in the economy or two sectors in the economy, and the describing of mainly of the saving consumption trade-off. And on the other side, you have a difference between optimization model and simulation model, which is really important because an optimization model produces a normative strategy, a normative scenario, and a simulation model is most of the time producing just a positive scenario. You put something in the model and you see how it works. It is most of the time because you can try, I think, as Patrick can make it with Paul's model, to try to iterate your simulation and to try to converge toward what is an optimal scenario, trying, for example, iterating on the different trajectories for a carbon price or something like that. Then when you use these models, so, sorry, for the previous slide, one thing that you can do is to understand what are the 5 families of the model, and I can spend more time if you want, but these are just general equilibrium model where energy is just one sector among others in the economy. And they have some difficulties to describe technologies. And so in the past 15 or 10 years, they spend a lot of time to include technology description in a general equilibrium. On the other side, here, you have bottom-up simulation work with a huge description, a very fine description of technologies, especially in the electricity sector, for example, but also in the biomass sector, in the transportation sector, etc. And they try sometimes to put a layer of economy on the top of that, but it's quite simple in general. On this side, as it is a question of optimization, the structure of the models are a bit simpler at the beginning. Here you have linear optimization with the Markov family model, which became nonlinear in some cases in the recent years. And here you have very simple macro optimization model like the Solo model and after the Dice and Rice models of Nordhaus in the States. And at the middle, you have some attempts to hybridize the model, trying to set a dialogue between precise bottom-up modules for each sectors and detailed economic simulation with many sectors also. But it is really hard stuff to couple the two things. Now I skip to another issue with two frequent flows that I know very well to have experienced it. The first one is data. When I was a modeler, I had no time for data. So I took a database that was existing, which was the JTAP database for the economy, the NRData database for the energy, and I was trying to put the data in the model, and I was running the model. And my issue was troubleshooting for the model, etc. And after that, when I had bad results or strange results, it was always a question of data, most of the time. So at the end, I had the impression to have spent my time not on the good issue, not on the good stuff, but too much on the equations and on the modeling troubleshooting. So the ready-to-use databases are really useful, I think, but in each modeling team, you should have, a reserved budget of time to check data, to see data, to look at the data, to compare databases between themselves, etc. But especially, obviously, you have no budget to do that, so it's real difficult, I think, for researchers. But you can make some double check. You can make a check-in on the database, on the data you put in the model. This is the first step. And you can also make a checkout on feasibility indicators as I was speaking, at the beginning. And the second flow is when you use the model out of its definition domain. And especially one example for me is recent attempts to use a macroeconometric model, which is at the beginning entitled to model short-term evolution of the economy, especially to check state budgets, sustainability, and something like that. You have something like that in the Trésor in France, a model which is called Mésange. And people working with Mésange know very well that their model is useful for 10 years and not no more. So you cannot use such a model to assess macroeconomic impacts of an energy strategy for 30, 40 years. It's just because an econometric model is taking the economy as it is now, okay, and just put some econometric equations describing a continuous behaviors of people from now for the next 20, 30, 40 years. So be aware of the model to use them on the right domain. Yes. I can spend 2 hours if you want, but so an illustration, because it was quite theoretical. I'm sorry for this first part. Funnier illustration of the necessary checkout and validity check of the model results is the debate we had during the national debate about future energy demand in France. And I think the debate is not only French. So I think you have shown this slide on Patrick's presentation yesterday. It was the 4 markers scenarios that had been shown in the debate to show the future of final consumption in France. And you see that if you correct this trajectory for a bizarre point here, because 2020 is tomorrow, so you know that the consumption in 2020 will not be there, and the cone here is narrower than that. If you check this point and you adjust this trajectory, you see that The uncertainty of our consumption is rather small in 2050. Okay, it's rather small first, and secondly, we have just a kind of bipolar world between those who think that we can reduce consumption from 20% and those who think that we can reduce halfway the consumption of France. And to judge that, I will not use a model. Will just look at the data in the past. What did we do in the past? Here you have a graph for the OECD as a whole, and not only French consumption. You see here in blue the GDP. I'm sorry, it's in French. The GDP line during the last 50 years. And you see here in green the electricity consumption, and in red the total energy consumption in France. Okay, and here it's an index in 1973. So you see that it's not very easy to say it, but before 1973, the energy demand was sticking GDP growth. For each percent of GDP, additional GDP, there had been 1% more energy demand. And electricity was growing even faster because electricity was growing in terms of share in the energy mix. Okay? Here you had, I think electricity was something like 4%, sorry, of the energy demand globally. Here it was 8% of the energy demand. So the share of electricity doubled in 15 years. And then if you guess that the link between GDP and total energy demand and GDP and electricity demand would have remained the same, the demand for energy and electricity would have been like this for energy and like this for electricity. But there has been an oil shock in 1973, and people realized that energy was quite expensive and could be finite. Then they make continuous efforts to reduce the energy consumption, and you see that it was the fact for energy and it was the fact also for electricity. Continuous energy efficiency gain that allowed the OECD countries to stabilize the consumption, the per capita consumption of energy. And in France, for example, in 1973, our fathers consumed just 30 megawatt hour of total energy per capita. Okay? And this is still the case. Obviously, our lifestyles have changed a lot. We consume much more energy services, but they are more efficient and the consumption is flat. Okay? So, can we do more now? This is the big question. Here you see the efficiency gains on buildings, for example, in France and in Germany from the Enadata database. Well, I think Enadata has not made its job on climate correction of this German curve, but it is climate corrected for France at least. Here you see that in 20 years we have reduced by 1/3 the mean consumption of 1 square meter in buildings. So it's not like in 2013, it's not like if we should begin to make efficiency gains. Okay? We have made efficiency gains a lot in the past, and we know that we can do a lot more in the future. But this picture is really interesting to see what can be the pace of energy efficiency gains with something like 15 billion of euro of spending in the French building, housing stock to reduce efficiency each year. So it's not just a bit, it's a lot of money. And we now reduce to 135 kilowatt hour of energy, final energy per each square meter. What can we do further? We know that one of the best renovation standards that we hope to see emerge in France is what we call BBC renovation for low consumption buildings in France. And the level is 80 kilowatt hour of primary energy by square meter. Okay, so it's around here. Okay, depending if you just we do not speak about electricity versus gas or versus biomass, etc. I think that we can go here to this level, but to go to this level, we have to retrofit all the buildings in France to this level. Okay, something like not far from 30 millions of buildings, or you can say 25 millions of buildings. And you have something like 5 millions already efficient, not far from this level. So one difficulty is that when you go closer and closer from this asymptote, because you still want to consume energy a bit in your house, it is more and more difficult to retrofit, to find the buildings, to retrofit them. And so what we expect, just from this perspective, without any modeling, without any normative view, etc., is that this space can slow down when we go closer to the asymptote. Okay? Or another way to say it is just it will become more expensive and more expensive to find the building and to retrofit it for less savings at the end for already efficient buildings.
Just a second. This is for new buildings?
No, this is the total fleet, total stock of buildings.
But I thought it was over 200.
No, the figures over 200 are primary energy. So you have this coefficient behind electricity, which said here I consider only the envelope and the equipment in the buildings, okay? Not the upstream energy mix, which is behind the energy you put in the building. Because my concern is just, should I retrofit the buildings? Okay.
How is electricity accounted for?
As a final energy as others. I mean, yes, it's all
Equivalent.
exactly. It is how much final energy go into the building. Yes, exactly. It's what is your on your bill of energy in your building.
This is heating and cooling.
Yes, heating, cooling, and water heating. But no electric devices because it's a different issue, I think. One of the things closer to us is what happened in the last 10 years. In the last 10 years, there were an apparent stability of energy consumption, remarkable stability of energy consumption in France. And even our colleague from the electricity grid in their last report last week or just a month before were saying, you see, the consumption is flat and we are going to begin to decrease the consumption. Well, what is puzzling is that effectively the consumption of total energy is flat. But during the last 10 years, the consumption of electricity was quite dynamic. But it hides two different dynamics. The first one is industry decline. You see here, the industry consumes 70 terawatt hour less than 10 years ago, and 60 terawatt hour come from the crisis. It is really puzzling. And on power, on electricity, this is the same picture for the electricity share. But at the same time, you see that the energy consumption in buildings was exactly the opposite, a growing demand of 60 terawatt hour. And this demand was mostly electricity demand for modern devices. It's not heating. It's at 90%. It is phones, computers, domestic devices, semi-durable goods, etc. So what will be the future? To my mind, it is really uncertain. I'm not sure at all that in the next 10 years the demand of energy and electricity will decline. I'm not sure that it will grow because it will be the interplay between the algebraic sum of these two trends. Will the industry rebound or have no future in Europe? And then you will see this trend continuing in the next years, but I'm not sure it's a good news. And will electricity demand for specific uses slow down or continue to grow with modernization, robots, automatic devices, and especially with perhaps a growth in tertiary sector, because all this growth was in the residential buildings, you know. But now you have a huge margin of growth in shops, in shopping center, in malls, etc. And you begin to see that, for example, in a car shop on the Champs-Élysées in France, because I think it's Audi or BMW that announced that the future shop will have no car inside, but just big, you know, 3D computer. Yes, to show all the models of cars, and you can just play with it, customize the cars, and see what you want to see now, just without having a stock of cars in the shop. So it will be interesting for the sector to have no car stopped in the shop, and it was also obviously very appealing for the consumer to see just all these cars different. But it will consume a lot of electricity. So, one indicator, 5 minutes, yes.
A bit less?
No, I will just end with that. And we can talk about energy demand after. We have further needs and unsolved issue in scenarios and in model works. The first one is still some progress to be done on learning curves. You know, this magic learning curves that are just saying that the future cost of energy is something like a function of experience. So you see the cumulated investment, for example, over the initial investment, and you have something like a beta here, which is the learning rate, or proxy of the learning rate. But this curve has no asymptote. The asymptote is 0.
I think presented that yesterday.
Okay, so it's not realistic, and you should have somewhere something like a best estimate of the asymptote, because we see that for all the technologies that are mature. Okay, but sometimes we do not know where is the asymptote, but we know that this is a very important parameter to set public policies, because if you have this curve or this one, the amount of investments to make the technology competitive will be very different in terms of cumulated investment over the next decade.
It has negative, is it right?
All right, yes.
Yeah, negative. Exponent.
Yes, exactly. The second subject is inequality and transfers. I had a word on that about Germany, where it's a big issue, but I think it can be a big issue also in France, where people that put PV panels on their roof are mostly rich people, but people that suffer from the surcharge, the upcharge of renewables are mostly poor people. So there is a small transfer for the moment in France, but it can be a subject. The third point is intermittency. Actually, the best way to talk about intermittency is out of the model, okay? Because we can talk about what is backup, okay? We can make back of the envelope calculus about what is the need of backup. And my own experience with our own model in EDF is that if you put some intermittent issues in a complex model, the results are not quite different from the simple calculus you can make on the envelope. So we can make the calcul together if you want. The only thing that it is really impossible to make on its own mind is the network. What will cost the grid reinforcement for intermittency? And the only information we have, for example, is what it is beginning to cost in Germany. Because in Germany you have now something like 12% of intermittent sources in the electricity mix. Germany is going to have more than 20%, 24, 23, 25, we don't know, percent of intermittent sources in the electricity mix in 2023, at the end of the nuclear decline. And this will cost, as far as the DENA has produced scenarios, it will cost 60 billions of grid reinforcement in the next decade. So it's a huge amount of money. And it is perhaps our main subject of concern for intermittency. The subject is not backup. We can build some additional fossil turbines that cost not a lot on investment and that will not produce very often. But network grid reinforcement and especially distribution grid for very decentralized sources is really an issue we have to work on. A fourth question is how we can go further in the projection of new electric uses in the buildings, especially robots and automatic devices. A fourth issue is obviously in Europe how the debt constraints and the liquidity issues or inflation issue, for example, or deflation issue will one day weigh a lot of investment capacity. The fifth one is the macro impact of energy prices. We always talk about the impact of energy prices on energy-intensive industry. But this is not only a problem for energy-intensive industry. Obviously, for them, it is a question of life or just delocalization. But for all the economy, energy is, either constrained constrained consumption for your building, for your car, or a factor of production for sectors. Energy in France, it's something like 7% of the GDP. 2 or 3% for electricity and the rest for fossil fuels. So if you double the price of energy, you see that it is not just harmless on the economic productivity of all the economy, not only on the energy-intensive sector. So the price is a huge parameter. And finally, we have a big issue to treat globally uncertainties, not just to forecast different scenarios that show how broad is the interval of future states, but to put uncertainty in the model, to see how people behave in face of uncertainty, to try to find optimal strategies in facing uncertainties, etc. So thank you for your attention.